All right. Questions about homework at all?
1, 2,
You have a question?
Did you guys say 7-11? Okay. I heard they said 7-11.
All right, 7-11. What is it?
Okay.
do you have that?
I got this. What's this? 7-11 says that suppose a link of WR137 wavelength operated at 7
Waveguide.
Waveguide.
This is 37, did you say?
Yes, sir. WR137.
WR137. We gotta look this up, the specs on that, but go ahead.
I will. You got 7 kilohertz frequency terminated. at
7 kilohertz?
Yes, sir.
Gigahertz.
Oh.
Gigahertz.
What did I say?
Kilohertz, you have wavelengths,
My
thousands of meters. Go ahead.
Terminating the short circuit. At what distance from the short circuit does the input impedance appear?
Very good question. This this also applies to transmission lines. So what they have is a waveguide, and you can think of a waveguide as a transmission line, pretty much. Now you have a load here, but this load is a short circuit. Right? Now I want you to think back in the days when you had when you were doing transmission lines. If this is a short circuit right here, and if you looked at the voltage magnitude on here, you all agree that everything would be reflected, first of all. Everything would be reflected. The reflection coefficient here is really ZL minus Z0 over ZL plus Z0. Since ZL is 0, it's just -1. It means the entire wave is reflected. In fact, it has to be -1 because if you take the incident field's value and multiply it by the reflection coefficient, you get the reflected field. Right at this point, this is Z equals 0. The superposition of those two will be 0. And if it's a short, it's got to be 0. Do you follow me, class? So when you look at this, if this is the 0 point, and you would graph the magnitude of V, you would get a standing wave pattern like this, where this is a minimum and this is V max right here. V max would be equal to 2 times V incident. It's just 2 times the incident value. That's its peak value. It's exactly 1/4 of a wavelength away from the 0 point. You follow me on this, class? And it kind of makes sense, doesn't it? A quarter wavelength is really pi over 2 degrees, if you think about it, right? Because a full wavelength represents 2 pi radians of space. Correct, class? Now, that's a maximum. If you keep going out a quarter wavelength, so you have a total distance of lambda over 2, then you have the null again. Basically, whatever's here repeats itself a full half wavelength away. You ever follow me on that? Now, whenever you have a transmission line, if it's greater than a half wavelength long, and remember that's wavelength in the guide for us, but this applies for both waveguides and transmission lines. If it's more than a half wavelength away, then you can start subtracting half wavelengths. Like if you have something 1.2 wavelengths, that's how long the transmission line is. To do the actual work you need to, the input impedance and all that, you can assume it's just 0.2 wavelengths. You can subtract 2 half wavelengths. Does everybody understand this? How many remember this from transmission line theory? Kind of, sort of. Well, at least you're honest with me about that. Now, what this one says, first he gives you the guide dimensions, and he gives you the operating frequency, right? We're going to go through this one. So for WR137 waveguide, I don't know this by heart, it's inches. It's like what? I'm thinking 0.05. Go ahead.
1.372 inches.
So A is 1.372 inches.
And B is 0.622 inches.
Where is
What?
that?
376.
All right, but just Google it. That's a standard waveguide. It's like American wire gauge has standards. This is a standard waveguide definition, all right? The cross-sectional dimensions. You can look it up. Because all this is standardized. All the component makers have to use that standard for a waveguide with that dimensions. All right, now that you have these two things, we've got to find what the cutoff frequencies are. And we know FC is equal, it's air filled, is that right? So we know we're basically dealing with the velocity C, right? So now you take C here over 2, square root, and then it's M over A squared plus plus N over B squared, and these are the actual cutoff frequencies for the MN mode. The first one you look at is FC10, that's a TE mode only. FC10 would be C over 2 times, if you look at this, it's just divided by A. And I went through the definition of how that's really representing a half wavelength, half wavelength fit across the diagonal. So what is that frequency going to be? Well, C is 3 times 10 to the 8th, but that's meters per second. Then I have 2, and I have to put A in meters. Can somebody do that for me? It's 0.1372 inches.
A in meters is 0.0348 meters.
All right, now give me this cutoff frequency for the 1.0. The 2.0 will just be twice that, and then it'll come to 0.3. Can you give that to me, please?
I think it's 4.29 times 10 to the
Who's
9.
talking? 4.29?
Times 10 to the 9.
Yep, that's about right. 4.29 times 10 to the 9. All right, hertz. The next cutoff is FC. The next one up is FC20. That's going to be twice that, double that. What do you get? You get what? Really 8.6 roughly? About that. There's a reason I'm doing this. I want you to see this. I'm going to try to represent this clearly. Now, if I just took a look at the modes of operation versus frequency, this is frequency, right? Here is going to be the FC, the cutoff frequency for the 1.0 mode. That comes down to be 4.29 gigahertz. The next cutoff you're going to run into is that one. That's up here. That's FC 2.0 mode. And this one is at a frequency of twice that, or about 8.6 gigahertz. And I'm just trying to show you the frequency where they are, right? Now, any frequency we operate on less than this will not cause propagation in a waveguide. Everybody got that? Anything less than this, it won't propagate. It'll attenuate like crazy, just short right up. It's called an evanescent mode. But anything between here and here will propagate in only the TE10 mode. Does everybody understand that? Only the TE10 mode. So our frequency of operation is 7.6, so it's right here, dead center, about dead in the middle, right? We can't go above there. Why can't we go above there to operate it? Anyone? Say it. What happens if I operate at 9 gigahertz in that waveguide?
Modes here.
Say again?
We'll have other modes.
You'll have more than one mode, more than one velocity the energy propagates, and you don't know how much energy or power is propagating at either of those modes. And you don't do that. You only want one mode for almost all cases. So that means it has to be between here and here for only one mode. And that also means that now I'm working with strictly the TE mode, not TM. So for TE, yeah.
What are those FCs?
I couldn't hear
I
you.
can't keep your hand around. What are the FCs? What are
Those are the cutoff frequencies.
Which
The
one?
well, the 1.0 is the lowest, right?
1.0 and what's the other?
2.0 would be double that.
Okay.
Y'all follow me? It goes 1.0, 2.0, and then 0.1. And that's how it's almost always in waveguides. If you've done those problems I gave you, that's apparent to you. All right, now, since it is TE mode, I'll try to write bigger, and I'm sorry about my handwriting. All right, now, we're going to go ahead and the next, well, what do they want besides that? What do they want?
Just the distance from the short that the input impedance appears infinite.
All right, well, this is a no-brainer, but we got to get the wavelength from the guide. So what I want to do is use this problem as a teaching moment, and I'm going to go through and analyze phase velocity, wavelength in the guide, beta in the guide, input impedance, the whole 9 yards. So we'll be able to figure out everything, all right? Let's go through it. For starters, for TE mode, as such, I'm going to get the one thing you're going to get all the time, the constant K, which is the square root of 1 minus, in this case, FC10 over F squared, right? That's going to be equal to the square root of 1 minus, and here the cutoff frequency was 4.29 gigahertz, but the actual frequency of operation is 7.6. So I take that and square it and take the square root. That's going to get my value of K. Somebody can give that to me in a second.
7.0.
7.7.
No,
0.7?
No, the frequency.
Oh,
Frequency of operation 7.0.
7.0? Oh, I'm sorry. I thought it was 6.
You're bigger.
Oh, 7 gigahertz, you're right, it's my bad. 7.0 gigahertz, all right. So that's gonna be a number somebody can give me in a heartbeat.
0.7902.
0.7902? 0.7902. Next thing I'm gonna go ahead and get is the ZTE. That's the, for the 1 mode, the actual characteristic impedance of the guide. This would be just like, it would be just like in a transmission line, you have a characteristic impedance, follow me? That's exactly what this is. So this is equal to the square root of mu over epsilon over K, isn't it, class? In this case, the square root of mu over epsilon is what, just eta of free space, isn't it, class? So that's equal to 120 pi divided by K ohms, and you can just tell me what that is. Is it like 400?
477.5.
477. So that's the characteristic impedance. Now, after that, the next thing I'm going to do, I'm going to need that. I'm going to go ahead and get the wavelength in the guide, and then I'm going to get beta in the guide. All right? Everybody follow me on this, class? So, yes, sir.
Can you explain what K represents conceptually?
Were you here last time?
I don't remember what
If you were here last time, do you remember how I said what this is specifically is going to be something that reduces either reduces the velocity of energy, or it increases the phase velocity, or it causes the wavelength to lengthen or beta to decrease. And this is due to the fact that when we go through separation of variables and we solve the whole equation, we finally get a beta z squared is equal to beta unguided squared minus, and it would be beta x squared plus beta y squared. And beta x is just m pi over a squared, and beta y is n pi over b squared. Well, beta z goes to 0 is the cutoff frequency. That's how we get that. But in doing so, we get a square root of 1 minus fc over f squared. I can go through it with you later if you want. All right, but it's ultimately from those equations, and we work those things, so I'm just going to leave it there. All right, we come down to here, right there. That's ZTE. Now, I'm going to get the wavelength in the guide and beta in the guide. First, beta in the guide is what? Do you remember this? It's beta unguided, right?
Okay.
Times K, right. Well, what's beta unguided? Omega times square root of mu epsilon, right? We have K. Do y'all remember this, class? It's omega times square root of mu epsilon. What does the square root of mu epsilon represent if we have air? It's just going to be c, isn't it? It's 1 over c, 1 over the velocity of light. Do y'all follow me, class? All right, that's the reason I'm using c. Next thing, but I got to multiply this times k. Now, omega is just 2 pi f, and f is the operational frequency. C is 3 times 10 to the 8th. K is that number 0.7902. So could you tell me what this is, beta in the guide? I can't hear you. What? Anyone? It's omega 2 pi f, 2 pi times 7 gigahertz. C is 3 times 10 to the 8th. K is 0.7902. Anyone?
145 or 3.
Can you say that again, sir? I think I'm 150.
15.
What say? One person.
115.85.
115.85. Thank you. Keep that in your calculator. Now, that's the beta in the guide, right? The wavelength in the guide would be 2 pi divided by beta in the guide. Because remember, beta in the guide is the thing that's going to be multiplying z, right? And when beta in the guide times z is equal to 2 pi, that's exactly a wavelength. And that's how you get the wavelength. So what do you get for that?
0.054.
Meters. So it's 5.4 centimeters, correct, class? All right. Everybody got that? That is the wavelength in the guide. Now the question was, how far away do you need to be in order that you would have an infinite impedance, right? Here's something I didn't show you. This is a graph of the voltage. Now, what was the impedance right here at the load? 0. What happens is when the voltage is a peak, it actually has an infinite input impedance. All right? That's what happens. I can prove that to you with the equations. Right here, it's infinite for a short there. How far away is that? A quarter of the wavelength in the guide, not the free space wavelength. wavelength of the guide. So you take a quarter of that, right? And that better be the right answer, or it's wrong on the book. So, what's that?
That's all right.
All right, well, that's how you get it. I don't know if Whitworth has that or not, Dr. Whitworth's book, but that's the way you get it with method. Now, I'm going to be asking you another question. There's two things I would like to know. What is the phase velocity in the guide, and what is the group velocity in the guide? Now, I talked about this last time, right? Phase velocity is kind of it's misleading because it can go to infinity, right? It's group velocity you want. This is the equation. If you don't know it, this is the equation used. Remember, if this is air-filled, so it'd be c squared. It's the velocity in free space. I'm sorry, the velocity in an unbounded media. So that's going to be 1 over the square root of mu epsilon squared, or 1 over mu epsilon. That is equal to the phase velocity times the group velocity, velocity of the group. Now, group velocity is the velocity energy actually propagates down the guide. Are you with me on this, class? Now when you take a look at this right here, the phase velocity from last time, do you remember what it was? Well, phase velocity, actually we could prove it from scratch, but it comes down to the velocity in an unbounded media, if it's air it's c, divided by k. Do y'all remember that? How many do? All right, from last time. It's really, you could put instead of c, put 1 over the square root of mu epsilon. So that's the velocity in any media, for any lossless media. Y'all are with me on this? The value k causes it to be faster than the speed of light. Follow me, class? In fact, at cutoff, it's going infinite. But if you wanted the velocity of energy, or the group velocity, what you do is take c squared and divide it by the phase velocity. And what do you get for that? Well, that's really k times c, isn't it, class? You all see that, class? So it's going to be less than the speed of light. Now that's the velocity you care about if you're an engineer, because that's how fast power goes down the guide. All right, that gives you, if you're doing any kind of split-second timing, that's what you need, that information. Okay? So we got waveguide, we've got wavelength, we've got beta. We know exactly a quarter wavelength away from the short. We have infinite impedance, correct, class? Everybody follow me on this one? Now, if we want the impedance anywhere, at any distance, a waveguide with any distance, then what you ultimately do is this, and this is one I don't want you to get hung up memorizing this. Working with it, you'll start using it. You know that Zn in general for any length is equal to Z naught. In this case, it would be the TE10. That's what goes there. If you're operating in 10 mode, that's what goes there. Follow me? Now you're going to take that and then you're going to multiply it by ZL. In that case, it's a short, right? ZL is a short. Then it's plus J Z naught TE10 times, and this is going to be the tangent of beta in the guide times the length of the guide over ZTE10 plus J, and this is going to be ZL times tangent of beta in the guide times L. Now he doesn't give a length, does he? He just says he wants to know the impedance, he wants a quarter wave, or excuse me, what distance away you have to be before the impedance goes to infinity, and I say a quarter wave, right? But this is the formula. If you use the right beta guide, ZL can be anything. If it's a short, you can just remove that and that, can't you, class? But this gives you the input impedance for any condition, any load, right? Any value of the characteristic impedance that you get. It's the ratio, really, of voltage to current traveling in that guide is what it amounts to. It's also the ratio of E to H, EX over HY. But when you do this, you got it, that's it. I'm trying to think if there's anything else I can ask you about, guys. We could talk about one other thing too, and this is kind of important. If you're going to be dealing, electrical engineers, you have to understand that electrical and computer engineers get involved with all sorts of aspects of projects, especially the smaller the company, the more different things you do. And one of the things you have to be aware of with waveguides especially is the problem of arcing, where you get arcing right from the top to the bottom. And the way that's caused is when the electric field strength goes beyond the breakdown strength of the air or the gas. Now, does anybody know what the breakdown strength of air is in volts per meter and at sea level right here? About?
Except for 1,000.
It's about 3 million volts per meter. Alright? Now that sounds like a lot, but if you just take plus or minus 1,000 volts on 2 points and you start bringing them closer and closer, all of a sudden you will see an arc. And that's when you achieve the breakdown strength of free space. You can do it with 100 volts, you can do it with anything. You'll see these visible arcs. I won't get into the physics of breakdown, but now if you know that, when you're dealing with power transmission in a guide, this is important. Well, transmitted power in the guide, normally what they do, and I'm not going to do this in length, I'll just show you a trick. Normally what they do is they say, well, the power density would be 1/2 the magnitude of the E field squared over eta, right? And that would be the eta of free space, by the way. I'm not going to go, you're not responsible for all this, just listen to me. That's true with free space, correct? Now, what ends up happening is this. This equation right here is watts per meter squared. What you have to do is find the E field equation in the guide, and then integrate it, square it, multiply it by half, and then divide by, and actually this is the power density. I'll use a small d here. That's in watts per meter cubed, pardon, not meter squared. What they end up doing is they take that and they're going to integrate it over a portion of the actual waveguide. Usually 1 meter long, and they keep the cross section. Then they say, what they end up doing is they're going to go ahead and do that, and they'll equate it. They'll equate the E field maximum to 3 times 10 to the 6 volts per meter, and they can figure out the power handling capabilities. Are you with me? I don't have time for it right now, but when you're dealing with this, you can actually get the power handling capability of the waveguide fairly easy for the 1-ohm mode. Did you have a question specifically?
What are letters in the absolute value bars?
That's the E field. It's just standard. What is the power density of anything? If you're talking about probably getting one, it's 1/2 the magnitude of the E field squared over eta, right? Well, what I'm showing you is that's the actual power density. Now, that E field, if you notice, there's an equational form for the E field in there, right? It has EZ and EX for the 1-ohm mode. And if you do that, you take both of those values of E field, you square them, but then what you're going to do is set the maximum value of that E field to be equal to 3 times 10 to the 8 volts per meter squared, and you will be able to figure out how much power that waveguide can handle. I'm not prepared right now because I don't have the stuff I need to show it to you in detail, but I can show you with the drawings how we actually estimate from the peak voltage across a waveguide what the peak E field will be. There's an easy way to do this, and I'll show you. Anyway, for power handling capabilities, this is the one thing. No matter how you figure it, you can't have an electric field inside a guide if it's air filled greater than 3 times 10 to the 6 volts per meter. If you do, you'll get arcing, all right? And it'll just short out. That will allow you to do the calculation for the maximum power that can flow. Actually, you know what I did there? That's flowing power. That is watts per meter squared. This is, don't worry about this, but power density is equal to 1/2 the real part of E crossed H conjugated, all right? That happens to be equal to 1/2 the magnitude of the E field squared over the magnitude of, really over eta, if it's lossless. And that would be in the AZ direction down the guide. But here's the thing about this, it's deceiving. You see the waves are ricocheting like this. Follow me? So you're going to have an EX as well as an EZ component. So in order to do that, you have to set both of those equal. You set one of them equal to 3 times 10 to the 6 volts per meter, then you'll solve for the other one. And when you integrate over the cross section of that guide, all right, the E field will only be EX. There'll be no EZ in that integration. And when you do that, the E cross H, that's the amount of power, the maximum possible amount of power you can push down the guide. Let me do that another time because I wasn't planning to do that, but I need to tell you that now, because he doesn't talk about it in his book at all, but you need to know that. He does not show you how to actually calculate the input impedance of a waveguide either. A waveguide is just like a transmission line. So that's the basis of that. Were there any other questions about the homework? I gave you the solutions. Most of it was plug and chug as far as I could tell. Right? only other thing I'm gonna tell you, TM modes, when they go to cutoff, the TM impedance is 0, whereas the T impedance goes to infinity at cutoff. Those are the two differences, the major differences, right? If you look at ZTE, it's always the characteristic impedance of free space divided by K, right? And the characteristic impedance divided by K, well, if K goes to 0, and that's what it would be at cutoff, the impedance would go to infinity. You follow me on this? The TM impedance will go to 0 at cutoff. That's the big difference you have to keep in your back of your mind. Where TM becomes important is when you have circular wavefronts. So if I have time, I'll cover that. All right, now, no other questions about the homework? All right. Well, I didn't have a chance to do separation of variables for the TM mode. Let me just, if you want, I'll go through this fairly quickly based on the fact that separation of variables is the same in all, but for either case, the difference is the boundary conditions. So when we did, before what we did is we had a, we went ahead with, we did the TM mode. I'm saying this backward. We did the TM mode. We ended up finding EZ was equal to some E naught, and it's going to be times the sine of M pi over A times X times the sine of N pi over B times Y, and it's times E to the minus J beta Z times Z. Do you all remember that class? And beta Z, just for the record, was equal to really the square root of beta unguided squared, right? Minus this beta X squared plus beta Y squared, or it came down to really, it was equal to, when all was said and done, beta Z came out to be beta unguided times the square root of 1 minus FC over F squared. If you look in the book, he has this, but I'm just showing you. That's what beta Z is. That's the beta Z that goes there. In his book, he doesn't even call it beta Z. He just leaves it as beta, which irritates me. It's beta in the Z direction. Follow me? Now, and that's beta Z. This is the one you use in that tangent equation. All right, that's the important. Now, having said that, that's for the TM case. When we do the TE case, all right, that means no electric field in the direction of propagation, the Z direction. Isn't that right? TM meant no magnetic field. TE is no electric field in the direction of propagation. Everybody got that? So what's the difference? Well, here, now since there's no electric field, we do HZ, and HZ is going to be equal to, I can give you the answer. I'll just tell you that the way we get this, because we're solving for HZ, is we assume it's some function of X, only X, some function just of Y, and some function just of Z. You kind of remember what I did before. And then you go ahead and solve the Helmholtz equation. Really, I'll call it the wave equation. It's going to be the del squared right here of, well, if I wanted to do the whole thing for you, I'd take curl of H is equal to J omega epsilon times E, and then curl of H is equal to J omega epsilon, and then curl of E is minus J omega mu times H, right there. Then the next thing I do, I say I have J times J is minus 1, with a minus sign is plus 1, so now I have omega squared mu epsilon times H, and this is HZ, by the way, and that's equal to this. Well, that's going to be the gradient of divergence of H minus del squared of H. And remember, this is HZ. You remember me doing something like that before? Only with E, EZ, correct? Now here at this point, something happens. Well, a lot happens actually, but we do two things. First of all, we're going to assume we're in the waveguide. There's no exotic materials, no bizarre materials. So what's divergence of H equal to and why?
0.
But why?
So about no magnetic monopoles.
No chunks of magnetic charge. Think of that. There's no singular plus or minus magnetic pieces floating around. And that means divergence of B or divergence of H would be 0, so I get rid of this guy. Now I'm left with that, right? Now I turn it all into one equation. I just do this. Now I say del squared of HZ plus that equals 0. Everybody okay with that? Now, my next step is what? Now I expand this in terms of what its definition is. So now I have derivative, second derivative of hz with respect to x, plus second derivative of hz with respect to y, plus second derivative of hz with respect to z, plus, and then I'm going to call a constant, I'll call beta unguided omega square root of mu epsilon. So this is really beta squared, so it's plus beta unguided squared hz equals 0. Does this look familiar to everybody doing that? Remember that for the E field? All right, now, because I said this, I assumed it was a function of x, y, and z. One more time we do it. When I take two derivatives of that with respect to x, right, now I get, and just bear with me on this one, x double prime y z plus x times y double prime z plus x times y times z double prime plus, and then it's beta unguided squared x, y, and z. And all of this equals 0. This should look familiar to you as well. What do I do next? We divide everything by x, y, and z, the functional form of x, y, and z. In doing so, we end up with this. And this is going to be y double prime. And this is going to be z double prime. And this is going to be just beta unguided squared. All equals 0, right? Don't hate me for doing this. I mean, you're going to be surprised how many times somebody brings that up, especially if you're working around physicists. Say, you guys don't know what you're doing. So, all right, now this. I speak from experience. Here, we set that equal to a constant, minus beta x squared. Do you remember doing that? Right? And you remember the reason why it had to be a constant? In your own words. Well, let's see. What if this function of x double prime x was not a constant? So I'll get a solution for a given y and a given z and beta unguided equals 0, right? Now if I change that value, all of a sudden it's not equal to 0, right? That means the only possible way this works, if that and that and that are constants, and all the constants plus beta unguided squared equal 0. Understand, class? And these are very specific solutions. So this we call beta x. This term is minus beta y squared. This term is going to be minus beta z squared. And that's plus beta unguided squared equals 0. Now, I'm just going to do one of these, but it goes for all three. When I take a look at this right here, that really represents the second derivative of x with respect to x squared, right there. Then it's going to be plus beta x, right, times x equals 0. Remember, that's the function x, functional form of x. It's not just the coordinate x. The small x represents that. Y'all with me on this, class? How many remember to that point, at least from last time? Now, there are three possible, don't you guys remember doing this, right?
Yeah.
All right, there's three possible solutions. I'm only going to show you the two that are pertinent. When I take a look at this, I know x here of x could be equal to some constant a times the sine of beta x times x plus b times the cosine of beta x times x. And here's where I'm going to make something known to you don't know, and it's very important you do know. And it's not stated strong enough in his book, in my opinion. When you have a waveguide, if this is the cross-section of the waveguide, now listen carefully. I'm just cutting a waveguide in half, and I'm looking straight down the pipe. In a waveguide, the E fields that at this point here must be 0 because they short out if it's a conducting waveguide. You got that? The E fields on this side must short out to 0, the E field in the Y direction. If this is X and this is Y, then EX is 0 at Y equals 0. It's 0 at Y equals B. The height of this is B, and this is A. Now, so you remember how we used those boundary conditions before, right? To get the actual E field in the Z direction. H field's different. Here's something real important. The H field is a relative maximum or minimum. I mean, it's going to be either a maximum value or minimum value, the tangent H field, on the conductor surface. Do you follow me on this? That means the derivative of that is 0. If you think about maximums, right? If you take the slope of that at the maximum, the slope is 0. Do you follow me on this, class? That means the derivative of the H field in the Z direction would be 0 at these edges. Do you follow me, everybody? Well, if I think about that, if the derivative is 0, so if I take x prime here of x, that's going to be a times what? Beta x times cosine beta x times x plus b times beta x times sine, it's actually minus that, sine of beta x times x. Do you all follow me on this? Now hear me. The derivative is 0, and if I look at this is the value of the H field in the Z direction. So follow me. When x equals 0, I'm here, right? Am I not, class? I'm all through here. This is x equals 0, correct? When I look at this equation at x equals 0, right, the derivative has to be 0. Isn't this automatically 0 here? Do y'all follow me in this? It's automatically 0. Now this one, we'd have to force it to be 0 by making a equal to 0. Do you follow me? That means this is going to be actually the solution that works, which means that the actual value of x is going to have a cosine variance, not a sine. Do y'all follow me on this, class? Well, what don't you see, sir?
Why does that,
You remember what I said, that the derivative of the x...
I'm not following the algebra. So the sine cancels out 0, the cosine doesn't.
That means this boundary is automatically enforced at x equals 0, right? We want this to be 0. Well, this one isn't. We'd have to cause a to be 0 to get that to work. That won't work, all right? So that means this is the only possible solution, or this is the only possible solution. Or really what I'm saying is the x variation here has to be a cosine. So just let me tell you this. This is going to be a cosine of beta x times x. It'll also be the same thing for y, a cosine of beta y times y. The variation in z will be the same as that for a wave for the t for ez in the prior one for the TM mode. It's minus j beta z times z, and there's going to be some magnitude here, h0, and that's equal to h z of x, y, and z. Now, I put that down here. I want to just tell you to get beta z, because I want to get this quiz out in a second. I just want to tell you this. Beta z is found, look here, look at this one, right? You remember what I said, that it's a maximum, right? It's a relative maximum. That means this beta x times a, when it's out here, right there, it's going to have to be equal to 2 pi over a. And I'm going to just get to the punchline here. What it really boils down to is that this beta x here is going to be equal to 2 pi over a, and this beta y is 2 pi over b. Follow me on this, class? Now that's because the boundary condition forced that to happen. If you take a look at the proof, it's very straightforward. All right.
The negative j and negative x to you, where did that come from?
Where?
Yes,
Here?
sir. Second line.
All right, well, what is the curl of E?
Curl of E.
Anybody know what the curl of E is? Minus j omega u times h. Right?
Yes, sir.
That's where it comes from. Good question, though. All right. Everything off your desks.